Welcome back, guys. Today we'll look at paper 11 of the May-June 2024 series. Now, as you probably know, the mark scheme has been released already, so feel free to check that out. However, these videos are supposed to be in addition to the mark scheme, because sometimes people look at the mark scheme, they see the answer, but they actually don't understand how they've arrived at the answer, or they don't understand why that's the correct answer. So in this video, not only will I try to actually write the answer, but I'll try to explain my reasoning as well. However, this video might go on quite long, so feel free to watch at 1.25 or 1.5 times the speed. Right, question 1. A student has a portable tablet computer. Identify two input devices that could be built into the portable tablet computer. Right, so when they talk about input-output, I like to think of the sort of human senses. So things like, sight, sound, touch, what are they, 5 or 6 senses. Right, so let's say for sight, right, so how we can see, let's say touchscreen, because this is talking about input. And then, if we're talking about sound, an input sound device, that's going to be a microphone. Obviously they've said only two, you can probably think of more. Like one common one I would also sort of be tempted to say would be accelerometer. Here I would always go with these two because, these seem to be the most obvious ones to me. But if they're asking for three, probably my third would be an accelerometer. And what an accelerometer is going to do, it's going to measure the acceleration. So specifically that can be used, obviously for, let's say, to detect movement, rotation. Because let's say if you're playing a car game and, you're rotating the screen, right, rotating the tablet, in order to drive the car or steer the car in a different direction, while the accelerometer is going to sort of measure that rotation. Also, when you switch your phone from, let's say, landscape to portrait or vice versa, the accelerometer is what is basically let's say the sensor that's actually detecting that. Right, so then, the next one, we want to identify one output device that could be built into the portable tablet computer. Again, of course we could say screen, touchscreen. However, since we've mentioned that already, let's try and say something else. Let's think, what's going to output sound? So that's going to be a speaker. Here you could also, of course, as well as screen, you could probably mention something like vibration or something. Maybe the tablet might vibrate. Although, maybe not. I guess some would, probably most of them wouldn't actually. Not really like a, games console or phone. Right, identify one type of storage device that could be built into the portable tablet computer. So let's say the three types where you've got solid state, hard drive, or let's say hard drive. Right, then also optical storage. However, if you think a tablet is going to be thin, so because it's thin, right, most likely we're going to want solid state. Let's say solid state drive. And of course we can call that SSD as well. The reason it's probably going to be SSD, one, they're fast, they're also, relatively high capacity, but mostly because they're thin. I guess they're also quiet, I guess if you drop them, they're not really going to damage, compared to a hard drive or optical drive, which again, if you drop it, it's going to damage. And you've got to think, you're just not going to be able to fit a CD player, inside a tablet. Likewise, a hard drive, they're quite big. Right, so two, hypertext markup language HTML color codes can be represented as hexadecimal. So just to recap then, HTML, this is the language used to create websites. And when it says color codes, usually they're going to be 6 hexadecimal characters. So let's say something like FF00, let's say FF. And what this is going to represent, the first two are going to represent R, right, so that's red. The next two are going to be G, right, so green. And then the last two are going to be B, so blue, right, RGB. And to be honest, usually we would also write a hash or pound symbol, just to denote that it's a hexadecimal color code. Although this itself is actually not part of the hexadecimal, of course, right, only these 6. So what this is saying then is saying, if we've got FF of red, right, that's going to be 255. Let me just make that full screen again. Okay, there we go. So it's saying, right, we've got 255 red, okay, then we've got 0 green, and then 255 blue. So effectively this is 100% red, 0 green, 0 blue. So that's going to be what, some, I guess, purple. Of course we can obviously change this. Let's say we've got an FF of red, maybe we've got like 4, 7 of green, let's say, I don't know, like A4 of blue, and yeah, that's going to be, well, whatever colour that is. Right, so hexadecimal then, well, we want to tick one box to show which statement about hexadecimal number system is incorrect. Right, so it uses the values 0 to 9 and A to F. Well, this is going to be correct. Right, it can be used, and I mean, obviously in the exam don't tick it, but I'm just, demonstrating. Right, it can be used as a shorter representation of binary. Again, this is also correct, because if we think, well, 2 to the 4 equals 16, so what this is saying then is, well, let's say this 4, right, okay, 4 bits, right, 4 bits is equal to 1 hexadecimal character. So again, we say, let's say like 1111, right, that's going to be F in hexadecimal. So yeah, obviously here it's like a shorter representation on paper. And that's another thing, right? I mean, don't say it uses less space. Okay, you can say it uses, less space on paper, but in a computer it's still going to use the same space, right? Because everything is binary. Right, so it's a base 10 system. Well, this is incorrect, because of course here it's going to be base 16. And it can be used to represent error codes. Well, this is correct, because, well, obviously, if you get an error code, sometimes it might be represented, I think sometimes they say like 0x, and then, I don't know, FF, whatever. And obviously this is going to be the hexadecimal error code here. I mean, we can also think, let's say it can be used for like IP version 6, right, so IP version 6, right, it can be used, well, for MAC addresses, obviously, color codes we've said, memory addresses, right, things like that. Right, denary numbers can be converted to hexadecimal. Convert the 3 denary numbers to hexadecimal. Right, so let's write out the positional values. Right, 16 to the power of 0, 16 to the power of 1, and 16 to the power of 2. So 16 to the 0, that's going to be 1. 16 to the power of 1, 16. Right, and then this one is 256. I think if we keep going, 16 to the power of 3, like maybe this is 4096. I'm going to put a question mark, I guess I would have to calculate that. Possibly this is correct. Right, anyway, so, right, first then we want to convert 20. So we can see here, well, obviously, right, 1 is not big enough, so then we have to go to 16. So if we think 16, well, we're going to have 1 16, and then, if we do, well, 20 minus 16, right, that's going to give us 4. So then what we're saying is, well, we have 4 remaining, so that's going to be 14. Right, the next one, well, again, 1 is not big enough, right, we need to go to this 16's position. And hopefully we can see here, well, 32 is just going to be 2 16s, right, and then, well, 0 remaining. And then 165, well, again, obviously, well, 16 is okay, but 256 is too big, okay, so that means, we only have to use this 16's position. And hopefully what we can see is, well, 165, we're going to have 10 16s, right, so 10 16s is going to be A, and then we're going to have 5 remaining, right, so just A5. Alright, just for practice, let's try one that's a little more difficult. So let's say something like 500. Well, obviously 16 is not big enough, so here we need to go to 256. But we only want 1256, because if we have 2, well, 2 is going to be 512, right, which is too big. So right, then we want to say, well, 500 minus 256, that's going to be 244. Right, then we want to think, well, how many 16s go into 244? And I think this is going to be F. Because if we think, well, 160 is 10 16s, right, plus 80, that's going to get us to 240. So that's going to be F, right, because, well, 15 times 16 is going to be 240. And then, well, then we just got 4 remaining. All right, so 500, right, should be 1 F4, like assuming I've not done any, incorrect calculation. Right, number 3, the binary number this is stored in random access memory. A logical shift of 3 places left is performed on the binary number. Right, give the 8-bit binary number that will be stored after the shift has taken place. Okay, so when I do these, let's try and, okay, there we go. I mean, what I like to do, and hang on, okay, there we go. What I like to do is just think, well, if we're shifting 3 places to the left, we can basically just delete these kind of first 3. right? Because obviously, well, they're all going to get shifted off. So let's just write down, this remaining, right? So 0, 0, 0, 1, 1. And then we have to think, because we're shifting 3 to the left, right, that means that 3 zeros are then going to get shifted in. So yeah, that's not too difficult, hopefully. Right, tick one box to show which statement about a logical shift left of 2 places is correct. Right, so let's think if we're shifting left by 1 place, that's going to multiply by 2. Of course, if we're shifting right by 1 place, well, that's going to divide by 2. So therefore, if we're shifting left by 2 places, basically what's going to, well, let's say sort of multiply, multiply or divide, by 2 to the power of n. So here, because we're shifting left 2 places, right, that's 2 to the power of 2, which is equal to 4. So yeah, that's going to be this one here. Now, this is kind of like assuming that there's no overflow, because if we try this in reality, let's say, well, 0, 1, 0, 0, and let's imagine we're only using 4 bits, right, and this here is the kind of overflow position. Obviously, if we shift this left 2, well, right, these two are going to get shifted out. So effectively now our number is just going to be, well, 0, 0, right, and then we're going to have 2 zeros, shifted in. So effectively what we've gone is, well, we've gone from, this here is 4, right, and then our new answer here is obviously 0. So yeah, this is not always true. I mean, like, what you can say, like, it's only going to be true, if, let's say, if no ones get shifted out. Yeah, because if a 1 gets shifted out, right, or let's say if a 1 gets shifted into this, negative position, right, if we're using 2's complement, then it means it's going to change. Of course, right, if it's unsigned, right, so if we're not using 2's complement, then, for example, if we have, like this, again, right, if it's unsigned, well, this would then, of course, be positive 8, so it wouldn't matter anyway. Right, the next one, so this binary number can be stored as 2's complement integer. Convert the 2's complement integer to denary, right, show all of your working. Okay, so again, I mean, yeah, maybe let's write down the positional value. So we've got, yeah, minus 128. Right, let's go 64, right, 32. Okay, right, 32. 16, 8, yeah, 4. Right, 2, and then 1. And yeah, let's fill in these correctly. Alright, so I mean, what we can do then, well, obviously, yeah, minus 128 plus 32, right, then plus 2 plus 1. So effectively, well, this positive part is going to be 35. So then we just got minus 128 plus 35. And I guess what that's going to be minus 130, minus 123, right, and then I think minus 93. Yeah, I think that should be my final answer. And of course, this in the exam, I would say double check, make sure you've not made an arithmetic mistake. Right, the binary number is measured as a byte because it has 8 bits. State how many bytes there are in a kibibyte. Right, so remember then a kibibyte is going to be, well, 1024. Now, if it's kilo, right, of course, well, kilo, that's just the regular scientific notation. So obviously, yeah, kilo, right, mega, yeah, giga, tera, right, etc. Right, so obviously, well, mega is going to be, a million, right, giga is going to be a billion. And, of course, we can also write this as well, 10 to the power of 3, right, then 10 to the power of 6, 10 to the power of 9. So, of course, yeah, incrementing by 3 each time, right, 12, 15. Right, whereas when we're doing, like, kibi, mebi, gibi, tebi, right, well, we can write these in, let's say 2, right, so 2 to the power of 10, right, that's going to be kibi. So, right, this is 1024. Right, when we're doing mebi, well, right, then it's going to be 2 to the power of 20. Right, gibi is going to be 2 to the power of 30. Yeah, tebi, 2 to the power of 40. And, you can also think of this in terms of, like, multiples of 1024. So 2 to the power of 20 is also equal to 1024, right, multiplied by 1024. Yeah, 2 to the power of 30, right, also, well, 1024, right, obviously times 1024 times 1024. So yeah, this can also be helpful in calculations, because sometimes they might have something like, I don't know, maybe 2048, let's say multiplied by 512. Now, probably to do that on a to do that without a calculator is, probably quite difficult. But what you can see hopefully as well, 2048 is basically going to be, 2 lots of 1024. 512 is going to be, half of 1024. So effectively, this sum is just equivalent to 1024, right, multiplied by 1024. So effectively, that's going to be in like mebibytes, or mebibits, mebibytes, right, depending on the unit. So yeah, you can think of you can think of these numbers as multiples of 1024, effectively. Right, the next question says, data packets are transmitted across the network from one computer to another. Describe the structure of a data packet. Right, so let's just try and draw a quick diagram here quickly. So first you're going to have the header, let's just call it H. Then the data or payload, let's call it P, right, payload. And then yes, sometimes you're going to have a trailer, right, not always. Now, if we think about the header, let's say the most common things is going to have the IP addresses. And in particular, it's going to have the source IP address, right, also the destination IP address. So the source, this is the sender, right, so us effectively. Then obviously the destination, that's who we're sending it to, like let's say the web server, maybe our friend, right, whoever. And then it can also include things like the, let's say the packet number, right, the sequence number. And I think for IG, that's all they mention. For A level, there's also going to be more. But I think, yeah, for IG, just mention those, right? So the source IP, the destination IP, and let's just say, the packet number. Right, then in the trailer, honestly, this sort of depends on the protocol. It depends on which layer of the kind of, IP stack you're in. But I think the sort of common one they say, CRC, right, so the cyclic redundancy check. Just kind of error checking method. So let's just say that, let's just say, I don't know, data packets, right, let's say contain 3 parts. And alright, here I'm just going to do it as kind of like a bullet point, right, so let's say header, right, and that's going to contain, let's say source, right, I'm going to do shorthand, right, source and destination IP, right, and the packet number. Right, let's go for the payload. Let's say data to be transmitted. Data to be transmitted. Or I'm not going to write this out. All right, let's keep the video a bit shorter. Right, then the trailer. Again, we can just say error checking. Right, so e.g. cyclic redundancy check, right, CRC. And I did actually check this CRC because, in the book it literally says that it just counts the number of ones, and I don't know, let's say we've got this binary here, this would literally put, and that's a 1 there, that would literally say the CRC equals 3 because 3 ones. Now in reality I did actually check because honestly this seems too simplistic, because let's say for example, I don't know, maybe this one changes to a 0 and let's say this one changes to a 1. Well, obviously the data is being corrupted, but this is still going to say 3, so it's still going to seem correct. So yeah, I think in reality the CRC is actually more complex than what they say in the book. It's going to use things like modulo 2 arithmetic, various other things. But yeah, I guess for the exam you can just say it just counts the number of ones, right? It seems that's enough detail. Right, packet switching is used to transmit the data packets across the network. Identify the device that controls which path is taken by each data packet. Right, so hopefully, again, let's say this is the source, right, this is the destination. Just, in the network you're going to have these things. And it's saying, what's going to decide where to send it to, right, the next hop. So of course these are going to be the routers. And the way the router is going to do this, it's going to have a routing table, and basically the routing table, it's going to map the, let's say the destination IP address, let's say our destination IP, and let's say then the next hop. So for example, let's say the destination IP address is 100 dot something something something, and let's say we're at this router here. Let's just try and draw this, right? Let's say we're at this router here. It will say, if the destination IP starts with 100, right, or I don't know, let's say it's in the range 100 to 200, right, then it will say send it to this one. However, let's say if it's in the range 201 to 255, right, it will then say, you know, send it to this router instead. So yeah, I mean, that's what a routing table is going to be, right? Just a mapping between the destination IP address and, you know, the next router to send it to, or well, yeah, sort of the next device to send it to. Right, C, serial data transmission is used to transmit data packets across the network. Explain why serial data transmission is used to transmit the data packets. Okay, so let's think about the advantages of serial. I mean, one, you say, well, there's going to be less interference, because of course, you know, you only need one wire, right? You're not going to have multiple wires that are interfering with each other. You can also say there's less chance of skewing, which means it can be used over a long distance. And just to recap what skewing is, like, let's say here we have two wires, and I don't know, maybe here they're sending the data like 1, 0, 1, 1, you know, something like this. Maybe this one is just sending, I don't know, this. Now, let's say, for example, this one is transmitting, I don't know, let's say a relative speed of like 100, well, I mean, let's just say a relative speed of 1. But let's say this one is transmitting at a speed of like 1.2, right? So it's going a little bit faster, which of course what that means is, well, you know, these bits here are going to arrive before, you know, these bits arrive, you know, obviously at the destination here. So what that means is, let's say, I mean, obviously if this keeps on going, what we might have is, let's say, like, I don't know, maybe bit 7 would arrive here. Yeah, or I don't know, or let's say here, you know, bit 8 might arrive at the same time as bit 7, you know, from here arrives. So the thing is going to get skewed, right? It's going to become, you know, out of sync, effectively. So yeah, I think we can say that. Let's say, right, serial. Again, I'm just going to sort of write in sort of shorthand. Serial is, well, all right, let's say serial data transmission, right, DT, right, is suitable for long distance. Right, because, and let's say because maybe because skewing won't occur, right? Because skewing won't occur. Right. So let's say, right, you know, hence no synchronization issues. Right, I think then we can mention that because it's serial, you know, we won't get interference or crosstalk. So maybe let's say additionally. Right, okay, additionally. Or let's say serial, serial data transmission, right, won't suffer. Right, won't suffer from crosstalk or interference. Right, interference / crosstalk, because there's only one wire. And maybe we can also mention, for example, the price or the speed. So of course it's going to be slower than parallel, but I guess we can say, well, the speed is reasonable, you know, and the price is cheaper than parallel too. Right, so also, I don't know, yeah, let's say speed, right, may be reasonable, or may be adequate. Right, and I don't know, I mean, we can just say sort of, you know, more simple and cheaper. Let's say it is simpler and cheaper than parallel. Okay, so I think that should be okay. Right, 5, a computer uses both random access memory and secondary storage. State the purpose of secondary storage. Right, so secondary storage, I mean, of course this is going to be permanent storage. So let's just say that, right, permanent storage. Permanent storage used to store, I mean, let's say, like, you know, files, data, programs. Right, let's say, once the computer is turned off, or once the device is turned off. Or I think here, well, here they mention computer, so we can, specifically mention computer. Okay, right, turned off. Right, one type of secondary storage is optical. Circle 3 examples of optical storage. All right, so when it says optical, well, of course, this means using light, right, or lasers. So right, that's going to be our compact disk. Well, let's try and go through them. So read-only memory. We can say obviously, yeah, this is like a solid state, really, right? It's just using, let's say, like flash memory, right, NAND memory. Again, SD card, well, yeah, that's solid state. Right, hard disk drive, well, that's going to be magnetic. Right, digital versatile disk, yeah, that's going to be optical. Blu-ray again, right, optical. USB, right, so that's going to be solid state, and well, solid state, of course, solid state. And if we just think about which of these is the best, well, CD is going to have the lowest storage, right? Then DVD is going to be in the middle, and then Blu-ray, this has the highest capacity. And the reason it has the highest capacity is because well they're using different let's say different frequencies or wavelengths of light. Let's say a CD. Well, a CD is using a wavelength with a kind of long, well, let's say a long wavelength like this. So yeah, a low frequency light. Whereas if we have a Blu-ray, well, a Blu-ray is going to be high frequency, which means a shorter wavelength. And because it's a shorter wavelength, well, that means that the pits and lands on the CD can therefore be closer together like this. The pits and lands on the Blu-ray can be closer together. Whereas, on a CD, well, the pits and lands have to be further apart, because of course, the wavelength is longer. Therefore, it's not able to like distinguish, basically, it's not able to, sort of differentiate or distinguish, if these pits and lands are too close together. That's not a very good explanation, but hopefully it makes sense. Right, then we want to explain why a computer needs RAM. Okay, so RAM is going to be temporary storage, and it's going to be where the currently used programs or processes, right, and data is loaded into. And I think we can also say it's going to be faster, because basically a computer can't directly access things from secondary storage. If we just draw a diagram, let's say let's call it S, right, secondary storage. Right, let's go R, right, that's going to be RAM, and then let's say C, right, CPU. So anything from secondary storage that we want, first it has to be loaded into RAM, right, and then from RAM it then has to go into the CPU like this. And again, likewise, if we're writing data, well, first we write data to RAM, then we write it to the secondary storage. There are actually ways to bypass this, but this is sort of the general model, right, the general way it works. Right, so explain why compute. Okay, so let's say first then, well, right, RAM. RAM is temporary. All right, temporary storage. Right, used to store. Right, used to store the currently. Let's say right, the currently running. Right, the currently running or accessed. I think running is okay. Let's say processes. Let's say processes and data. So let's mention. Alright, well, okay, yeah. So let's mention this here. Right, the CPU can't directly access the secondary storage. Right, can't directly access secondary storage. Right, okay, and let's say, I know, hence, hence RAM is needed as an intermediate. Let's say, as a faster intermediate. Right, so let's see what we've got here. I think temporary storage, that should be 1 mark. Probably processing and data, that should be another mark. And then I think speed, right, that should be another mark. So yeah, hopefully that should be 3. And I would say, with these explanation questions, right, that's probably quite a good thing to do, where just, read the answer again and like tick off what you think they would probably give the marks for. Obviously thinking like making sure you've got the keywords, that they're probably looking for. Again, the keyword's probably temporary, right, processes data, and then something mentioning speed or faster, something like that. Right, the computer processes instructions using the fetch, decode, execute cycle. Draw and annotate a diagram to show the process of the fetch stage of the fetch, decode, execute cycle. Right, so this one's a bit difficult. Let's just try and sort of draw out this. Well, first we've got the PC, the program counter. Then we've got the MAR. Then we've got the MDR. And then here we've got the CIR. Right, and of course all of these are going to be in like the CPU. I did check the mark scheme. They've got a slightly more detailed diagram. But let's just say here, right, first we've got the PC, and I'm just going to sort of draw that in a box. Then we've got the MAR. Then we've got the MDR. And then here they actually say the CIR, right, that's going to be inside the control unit. I think honestly, you wouldn't really need to do it inside the control unit. But yeah, maybe they'll just give you an extra mark if you do. Alright, so let's just do that as well. Right, and then I remember they actually do have RAM here. Because, obviously, you're going to be fetching the instructions from RAM. Yeah, and here we're only talking about the fetch, right? So obviously we're not going to be writing anything back to RAM. Okay, we're only loading, loading the instruction from RAM. Right, so first what's going to happen then, let's say the value in the program counter, right, is copied into the MAR, because let's say we're on instruction 100. Well, this 100 value is copied into the MDR, the MAR. And I don't know, maybe let's label this as 1, and then we'll just explain this. So let's say step 1. Let's say, let's say next. Let's say address. So address. Right, address of next. Let's say NI. Right, next instruction. To be executed. Let's say copied from, and that's going to be PC. To MAR. Then we want to say stage 2. Well, stage 2 is going to be. Basically it's going to be the instruction at the address, stored in the MAR, is copied into the MDR. So let's say that, instruction. So for example, let's say in the MAR we've got 100. Well, what's going to happen then is we're going to go to, memory address 100 in RAM, and then, that's then going to be copied here into the into the MDR. So maybe we can just delete this arrow. So instruction at address. Instruction at address stored in MAR. Let's say is copied. Into MDR. So for example, let's say that the instruction here, this is memory address 100, because maybe there's more up here. And I don't know, maybe this has the instruction add, let's say 5. So effectively, this add 5 instruction is going to be copied into the MDR. Or I think for 3, we can probably then say the PC can be incremented. Or let's say PC or program counter is incremented. And this means it's going to be ready for the next instruction, because it's going to go from 100, up until 101. Then we can say 4, and 2 and 3. 2 and 3 can happen simultaneously. So we could say this, simultaneous. Simultaneous. Then we want to say. So the next one then is going to be the instruction from the MDR is then copied into the CIR. So instruction in MDR is copied into CIR. Alright, and then that's going to be it, because when it's in the CIR, then the instruction can be decoded. And then once it's been decoded, then it can finally be executed. But of course, we're only talking about the fetch stage, so that's why we only have these 4. 6. A computer needs firmware and system software to operate. State the purpose of firmware. So firmware, if we remember the definition, and you can kind of think, obviously soft is, soft, like squidgy. Obviously, yeah, hard is well like a table, right? It's solid, and you know, firm is going to be somewhere in between. So effectively, firmware is going to be like between the hardware and software. So in particular, well, we can say this then is going to be the low-level software. Right, low-level software used. Right, let's say to directly control and communicate with. Right, directly. Control and communicate. Communicate with the hardware. Right, then we want to give one example of firmware. So, I think the most common one, we can just say the BIOS. Alright, yeah, that should be a B. Right, the BIOS, well, the basic input-output system. And what this is going to do, this is going to include the bootloader. So the BIOS, well, when it says, basic input-output system, it's going to do things like, checking the peripherals, right, checking the input-output devices. So, it will make sure, is the RAM working, is the keyboard working, right, is the hard drive, the mouse, the screen, it'll just do a kind of, let's say, error check of all of this hardware, right, make sure it's all working. If it is working, obviously some of them will be fatal, like let's say, for example, if the RAM is not working, right, well, that's going to be a fatal error, and, hopefully it will give you an error message. Maybe it might just crash, just blue screen of death. If it's something like, the mouse is not working, well, then it won't actually tell you, because of course you can just like unplug that mouse and like plug in a different mouse. Once it's done this, right, it's then going to do, the bootloading process. And what that's doing is, it's going to load the operating system from secondary storage into RAM, because maybe your operating system is, well, either on your hard drive or SSD. And of course, then it has to be loaded from that into RAM, for your computer to actually start running properly. Right, so the next one, give two examples of system software. Now, I guess just quickly, another example of firmware, right, could be a driver. So yeah, device driver. Again, maybe a like graphics driver for a screen or graphics card. Yeah, maybe a mouse driver, right, like Wi-Fi driver. Right, so give two examples of system software. And this one I did actually check the book. So if we see here system software, but they say, well, the operating system and also utility software. Obviously, yeah, hardware they have is the lowest level, right? Then it's going to be system software. If we want to make this more detailed, we can also add firmware here in between. And then, yeah, finally, you've then just got the application software. So things like, I guess, office programs, games, yeah, browser, database, yeah, etc. Right, so let's just write this then, the operating system. Right, and then also utility software. And I think, a lot of people get confused about what utility software is. I think the sort of simple definition I've heard is that it's software that's used to, let's say, improve the performance, and let's say just to sort of manage the system, really. So some examples, as we can see, well, we've got a virus checker, so antivirus. I think everyone knows what an antivirus is. Let's recap the way it works, right? There's sort of two ways. One, it can have a database of sort of known viruses, and then it will like scan the file that you've just downloaded. And of course, if it sees a similarity with a file already in the database, right, then of course it can flag it. Right. Well, another way it can use is a heuristic check. And heuristic, this just means behavior. So let's say there's some process running, and let's say the antivirus or anti-malware, that's detecting that this process is basically reading a load of files. It's then modifying the files by some like let's say encryption or something, and then it's just writing those files back. Well, hopefully the anti-malware would realize, right, this is going to be a sign of ransomware. So based on the behavior of that process, it can detect this is possibly ransomware. Of course, it might not be. It might be I don't know. You're just like compressing a load of files, or you're like legitimately encrypting them. But obviously, maybe it's not. So maybe it might just flag a warning. Right. Another example of a heuristic. let's say you have some process that's sending like gigabytes and gigabytes of data to like one particular IP. Now, again, maybe that's a legitimate file upload, but maybe it's also, you know, some spyware that's just like sending all of your files to the like remote host, or yeah, the hacker's computer. Alright, defragmentation. Let's say if you have a hard drive, and again, defragmentation is only used for hard drive, or defragmentation. Right, so let's say you have a file and it's a big file, like maybe some of the file is here, some of the file is here, you know, some of the file is here. Well, this is going to be slow because, you know, first let's say the read-write head has to move to, you know, this position, right? Then let's say it's got to move, you know, to this position. I mean, when I say move, of course, the read-write head can only move sort of up and down like this. So, you know, it's also got to wait for this part of the thing to spin around. So effectively, this is going to be slow because while the read-write head is moving, it's also waiting for, you know, that part of the disk to sort of spin underneath the read-write head. So effectively, obviously, it would be quicker if instead of going like 1, 2, 3 like that, we could just put, you know, say this is part 1, or this is part 2, this is part 3, and of course we just, you know, combine them all together, because then it means the read-write head doesn't have to move. So that's what that's what defragmentation is going to do. Right, it's just going to, you know, obviously, yeah, defragment, so kind of like unsplit the files, right, just put them together again. Right, so disk content analysis and repair, like, yeah, maybe you've got some corrupted files on your system, and, you know, of course, this can just check. It can, it can use things like a, let's say like a checksum, right, in order to check the file contents are correct. Right, let's say file compression, obviously, if you want to reduce the file size, file management. So again, obviously, while just compressing, you know, moving files, maybe transferring them, you know, stuff like that. I mean, backup software, I think everyone should know. Security, so like, I don't know, managing permissions, passwords, maybe some like biometric, some hardware security. I mean, screensavers, you know, these are not actually used anymore. I'm not sure why this is in the book, to be honest. However, I think, I mean, the reason these were used is because with the old CRTs, so the cathode ray tubes, I mean, CRTs, these are basically, you know, these big, like, fat, let's say, like, the fat screens. So, you know, whereas now most people have a nice, like, thin laptop screen or a thin desktop screen, or, yeah, even TV, you know, these would be, I'll draw it from, like, a side-on, and you'd often have it where, this is maybe not a good drawing, but this is kind of like a side-on, right, where, you know, this is the screen here, and, you know, it's obviously going to be really deep, because what you'd have like a kind of electron gun, and yeah, this electron gun is going to be firing electrons onto the screen. Now, if you're displaying the same picture on the screen for a long time, then, you know, those electrons can actually, like, permanently burn the image into the screen. So yeah, that's why you have a screensaver, which is just like an animation, which is just like constantly moving, constantly changing, which means that you don't have like the same, let's say the same image displayed on the screen constantly. Yeah, which means that obviously it's not going to get burnt onto the screen. Right, but again, that's kind of a long detour, just explaining some of the utility softwares. Question 7 says data is encrypted to keep it safe during transmission. Complete the paragraph by asymmetric encryption. Use the terms from the list. And some of the terms in the list will not be used. You should only use the term once. Alright, so let's just recap both. I mean, if we've got symmetric, right, so not asymmetric, but symmetric, well, then you're going to have obviously A and B. And of course, right, they're both using the same key, right, both using the same private key. However, if we have asymmetric encryption, well, let's just do it here. Right, so asymmetric encryption, and let's say that A is sending to B. Well, A is then going to use, let's start. So first we've got the plaintext. So the plaintext is, you know, the actual message we're sending. Right, so then what's going to happen is, A is going to use B's public key. So let's say pub key. Right, so A is going to take A is going to take their plaintext. They're going to encrypt it with B's public key. When they do that, of course, well, now this is going to be called the ciphertext, right, the encrypted message. They're then going to take this ciphertext, they'll send it to B, and then what B will use is, well, B will then use its private key. Right, they'll use their private key in order to decrypt their, in order to decrypt this ciphertext. and then yeah, once they've decrypted it, well, then they'll get back to the plaintext. So I think that's what we just want to say. So we want to say, right, something is encrypted into something using a something. So as we said, well, it's going to be plaintext. Alright, so actually I'm just going to sort of do an arrow here. Alright, so yes, this one's going to be plaintext. Right, plaintext is encrypted into ciphertext. Right, and that's going to be using a public key, and in particular this is going to be the receiver's public key. Right, the encrypted data is then transmitted from the sender to the receiver. The encrypted data is then decrypted, right, and that's going to be using a private key. Alright, so let's just go through all of these. I mean, so asymmetric, well, we've said, right, it's going to be encryption using the public and private key. Now here we've only looked at A encrypting and sending to B. Now let's say if B also wanted to, send something to A, well then that would mean that A would also need, a public key, right? A would also need a private key. So effectively then we've got 4 keys, right? If we want two-way communication, this is going to require 4 keys. Whereas if we have symmetric, we only need 1 key because yeah, they're both using the same, let's say, private key. Right, I mean certificate, well, yeah, if we think about digital certificates, this is just a way to authenticate, like, let's say a person or, a website. Well, I mean really more like a web server. And I mean in the digital certificate, well, this is going to include things like their public key, but it's also going to include like their digital signature, and also some other like identifying information. For example, the I don't know, maybe like a telephone number or an email address of the owner of this. Yeah, maybe like a, I don't know, some like business ID number or something like that. Yeah, just to verify their identity. Right, I mean ciphertext, we said that's obviously the encrypted data. I mean decrypted, we're obviously going from the ciphertext back to the plaintext. Yeah, encryption obviously from plaintext to ciphertext. I mean parallel key, I think that doesn't exist. I've never heard that term. Obviously plaintext, the original data. Yeah, private key, obviously a key that only only that person knows. Yeah, I mean protected, I don't think I've really heard that. Obviously a public key, well, that's something that anyone can access, right? So not only A and B, but also let's say we have another person like C, right? Just some completely random person. They can literally just go to B and ask them, what is their public key, and B will just send it, because like usually this will just be stored on a website. Like for example, let's say we have like Google. Obviously I'm not sure the exact address, but let's say google.com, let's say public, right, .key. So, I mean, basically anyone can just, download this public key, because it is literally just like a, well, yeah, it's just a file right, on a web server. Right, I mean, serial key, again, I've never heard of that. And well, symmetric, yeah, as we've said, right, just using 1 key. Yeah, 1 key for both encryption and decryption. Right, a farmer uses an automated robot to plant seeds in the field. State what is meant by the robot being automated. Okay, so let's say maybe the robot, I think, yeah, let's say operate, that's probably a good word. The robot can operate, let's say, yeah, completely by itself. Right, yeah, I mean, it's really difficult to sort of draw with this tablet. Right, can operate completely by itself, let's say without, right, without human intervention, or yeah, without human control or intervention, right, operation. Right, then we want to give 3 characteristics of a robot, and the way I remember this, well, just PEM. So P, right, it's going to be programmable. So, and let's just sort of explain this briefly. Can be, I don't know, can be programmed, right, to perform specific tasks. Right, so E, well, that's going to be electronic. Right, yeah, well, let's say consists of electrical components. Right, electrical components. And what M, right, that's going to be mechanical. And you know, when we say mechanical, right, this also means that it can move. So you know, you can sort of write it as like like this, right? It's mechanical, right, and it can move. However, I notice in some mark schemes they don't really mention movement specifically. They just mention, yeah, programmable, electronic, and mechanical. So obviously mechanical, yeah, that can be like I don't know, like an actuator or some, you know, movable arm or something like that. Yeah, and you can explain that if you wanted. Right, the robot plants seeds and stops when it reaches a fence. It then turns and continues planting seeds. The robot uses sensors and a microprocessor to know when it's reached a fence. Right, explain how the robot uses sensors and a microprocessor to know it's reached a fence. Alright, yeah, I just took a little drink. Right, so here then, I mean, you could mention it's using like an infrared sensor. However, I will admit this one I did check the mark scheme, right, and they do specifically say proximity. So let's mention that, right, let's say uses a proximity sensor. Although to be honest, yeah, I think maybe if you say uses like an infrared sensor to detect the distance, right, maybe they would also accept that. Because honestly, I mean, that is what a proximity sensor is going to be. You know, it's kind of like radar, where obviously it's going to send out a signal, and this could be like radio waves, it could be a sort of ultrasound. Obviously it's going to sort of measure the time it takes for that signal to bounce back, and yeah, based on that time it can obviously work out the distance. Right, so uses a proximity sensor to detect, or let's say, well, to continuously continuously detect distance from fence. Or let's say maybe these signals, right, these signals will be analog. Let's say so will be converted to digital. Right, will be converted to digital. Right, using a ADC, or using an ADC. Let's just put in brackets, right, analog. Right, analog to digital converter. Right, so these signals will be analog, so will be converted to digital using an analog to digital converter. Right, and let's say and sent to the microprocessor. Let's just say MP. Right, okay, so microprocessor will then, I mean, let's say maybe we'll compare these signals with the expected values. Right, we'll compare, yeah, let's say this signal, yeah, or I don't know, maybe this value with expected values. And yeah, let's read the question again just to see what exactly we want to do. Okay, right, so it's going to say, well, it's just going to, yeah, stop and then turn around, okay. Whereas the microprocessor will compare this value with expected values. Right, and let's say and if too close. Right, if too close to fence. Let's say we'll send a signal. Yeah, I don't know, maybe send a signal to the engine, or yeah, I don't know, maybe the engine to sort of stop or something. Or just say, yeah, send a signal to the, you know, robot movement, whatever it's going to be. Well, let's say, yeah, send a signal to the engine to slow down, or yeah, well, let's say to stop. Right, let's say and the wheels to turn around. I mean, yeah, I know, or let's say to stop and turn around. Or let's say maybe engine, yeah, I mean, let's write it like this. Because obviously, like, in order to turn, the engine can't stop. you know, obviously turning actually requires the engine to be on and running, right, in order for it to move. Okay, yeah, no, I think obviously this is not really the most important part, really, you know, how the actual engine moves, or, you know, how the robot moves. Yeah, to turn around. Yeah, okay, and then I think we can say, so this is what happens, obviously, if it's not in the expected range. I mean, all right, let's say here, I know maybe the robot, yeah, I know, let's say the robot will now, you know, plant seeds in the other direction. And I mean, so yeah, again, right here we've mentioned what happens if it's not in the expected range. Let's say, right, if sensor reading, okay, right, hang on, maybe if sensor value, right, is in microprocessors, let's say normal or expected range. Well, then we can say, yeah, like then nothing will happen, or yeah, slash the robot will continue moving as normal. Or let's say, yeah, the robot will continue in its current direction. Let's say, yeah, continue moving in its current direction. Okay, I mean, so hopefully that will be enough here for 6 marks. Although for these questions, you know, definitely check the mark scheme as well, right, just to see what they say. Right, give 2 advantages of the farmer using an automated robot to plant seeds. One, we can say, well, it's cheaper. I mean, well, let's say cheaper in long term. Right, let's say since, let's say since, you know, no labor costs or no salaries to pay, or maybe, yeah, no employees to pay. Right, I think another one we can say, well, they can work, you know, 24/7, 365 days a year. So yeah, maybe we can call that like availability or something. Right, so yeah, I can work, well, let's say, yeah, 24/7, 365 days a year. Right, and then I think for other ones, you know, you could probably mention something like accuracy, or maybe consistency, in that, you know, they're always going to do the same thing over and over. Whereas, you know, a person, of course, I don't know, yeah, maybe like different farmers, you know, different people, they might be doing slightly different things, which, yeah, I guess that could cause problems because, like, obviously, if you're doing a farm, you know, you want to have the seeds planted like the correct distance apart, you know, the correct depth in the soil, all this kind of thing, I guess. Right, give 2 disadvantages of the farmer using an automated robot to plant seeds. Right, so I mean here, you know, I guess an easy one, like, let's say high initial setup cost, or let's say initial, right, setup, and purchase cost. Right, and then I think another one you can talk about, well, of course you could mention, you know, maintenance costs. If they break, you have to fix them, you have to pay. But I mean, that's kind of similar to one, right, just talking about the price. So let's probably mention, like, if they go wrong, or if there's, you know, some unforeseen situation, like these robots, they're just going to continue planting the seeds, like, even if it's wrong. And if that happens, you know, you have like thousands and thousands of seeds planted, but, you know, obviously there's been some problem. But yeah, obviously the robot's just like continued regardless. Whereas I guess a human, they kind of they can like adapt to, you know, sort of situations. They have their common sense, their logic, right? So they're obviously not going to continue like if something is obviously wrong. So let's try and mention that. If conditions are abnormal. Let's say abnormal, like unexpected. yeah, or something goes wrong. Right, let's say, yeah, robot may continue planting. And let's say, I don't know, yeah, this might have to be undone, you know, would be time consuming and expensive to undo. Right, so yeah, would be time consuming right, and expensive to fix. Yeah, or, I guess we can also say you like to rectify, right, so to put correct. Right, the robot is adapted to have machine learning capabilities. Explain how this will improve the robot. Okay, so we can mention that the robot will be able to sort of learn from its past experiences. So maybe, for example, I don't know, maybe it looks at a certain type of soil, like a moisture level, or some kind of, I don't know, yeah, maybe just the distance, right, the placement, you know, whatever. But, you know, based on this data, it can realize, well, like which conditions will create like the optimum growing of the plant. And then, of course, it can use that, you know, when it then plants the next lot of soil, the next lot of seeds the next time. So yeah, let's try and say that. Let's say the robot. Let's say the robot can take. Yeah, I don't know. Maybe take the sort of planting data and output or something. Or I don't know. Yeah, maybe take the experience. Yeah, I think let's say this, right? Let's say the planting data. And let's say maybe and outcome. I guess we can say and growing outcome. Yeah, as sort of experiences, or yeah, let's say as experiences slash data to I don't know, yeah, to learn from. Right, let's say hence. Right, hence the next planting time. Okay, right, the next planting time. Yeah, I don't know, maybe it can plant according to its learnt. Yeah, it can plant according to maybe it's learnt, I don't know what, like experiences or like, yeah, I don't know, conclusions. I don't know, let's say experiences. That's probably not the best word. Right, so it can plan according to its learned experiences, right, and hopefully we can, I don't know, say, let's say like the yield or, yeah, efficiency. I don't know, yeah, let's say, right, the yield, right, efficiency of the farm will increase. Alright, so again, you know, probably not the best grammar and things, but hopefully that's got all of the details. Right, 9, a company owner has installed a new network. Data is correct before it is transmitted across the network. The company owner is concerned that data might have errors after transmission. Right, we want to explain how the data might have errors after transmission. So let's say there could be a hardware error. Right, there could be a, right, let's say HW, right, hardware error. Yeah, which has resulted, let's say which results, okay, resulted in, or let's say data loss, right, or data corruption. I mean, I think they also do mention like data can be added, although honestly it seems rare that, you know, the hardware error might cause data to be added. I mean, I guess it could. So let's say like data loss, data corruption. Right, or data addition. So I mean, honestly, I think that's actually enough for 3 marks. But let's try and mention another example, right? We could mention, let's say, malware, right, or some man-in-the-middle attack. So let's yeah, I know maybe there could also be malware. Be malware on the network. Or let's say malware, right, or a hacker. And let's say here, right, man in the middle. I mean, I think man in the middle attacks, they're not really mentioned in the book. But I mean, yeah, if you want to search that up, right, just go on YouTube, type in man in the middle attack. I mean, it's pretty simple what it is really. Right, so there'd be a malware or a hacker that is maliciously modifying, or yeah, I mean, right, maliciously modifying or deleting data. Right, modifying or deleting data. Right, okay, and I think you can also mention maybe like a configuration error. For example, let's say a firewall which is actually dropping packets, kind of unexpectedly, because yeah, maybe the network has been configured incorrectly, and maybe the filter is too strong. It's kind of like filtering packets that it shouldn't be. So let's mention that. Yeah, maybe a configuration error. Right, yeah, let's say e.g. Let's say FW, right, firewall, that is dropping, right, dropping, and let's say legitimate packets. Yeah, so basically it's kind of flagging these legitimate packets as being, malicious or illegitimate, yeah, by mistake. Right, then a big question. So the company owner decides to introduce an error detection system to check the data for errors after transmission. Right, the error detection system uses an odd parity check and a positive automatic repeat query, or ARQ arc. Describe how the error detection system operates to check for errors. And as we can see, I mean, this is an 8-mark question, and honestly, I'm not sure I've ever seen 8 marks in IG before. So what I'm going to do here, I'm just going to try and draw this. So what they're saying then is, well, again, right, let's say we've got the sender, right, then we've got the receiver. So well, they're going to take the data, whatever that data is, they're then going to do odd parity. So of course, just counting the ones, right, making sure it's an odd number of ones. Well, not really making sure it's an odd number of ones, but let's say here we've got our data like 1, 1, 0, 0. Well, of course, since here we've got 2 ones, right, that means we then want a 1 as the parity bit, in order to make an odd number of ones overall. If instead we had, 0, 1, 1, like this, right, so 0, 1, 0, 0, well here then of course our parity bit is going to be 0, because yeah, this gives us an odd number of ones overall. So once it's done that and added this parity bit, well then it's going to send it to the receiver. Now if the receiver receives it, and if the receiver then let's say validates the data, verifies the data, and when I say verify, I mean verifies that it's using odd parity correctly. So if it gets that, well then it's going to send a positive acknowledgement back. So let's say let's say positive acknowledgement. Of course, if the sender receives this positive acknowledgement, well then it's going to send the next lot of data, and of course this is just going to continue. However, let's say the receiver receives it and the data they receive is this. Well, here it's going to check this and it's going to think this parity bit of course should be a 1. So that means either some of these bits have been corrupted, or this parity bit itself has been corrupted. Right, so here of course there's not going to be it's not going to be correct. So then what it can do, well I guess either it can ask, it can say, hey, there's been an error, like just resend, and of course then the sender will resend, or it just won't do anything, right? And then the sender will wait for let's say it waits for like 2 seconds, and if it's not received anything after 2 seconds, well then it's going to resend again. And of course this will continue until the receiver gets the correct data. And yeah, I mean, and what we can say then is, let's say there'd be like a timer or like an error count. So let's say if they haven't, yeah, I mean it kind of depends, right? Because I mean this can work just using time. It can work, using a counter. I mean I did check the mark scheme. I think they say timer. So let's say for example this sender sends it, and well, for instance we'll just say the time starts at 0. Now if the receiver then sends a positive acknowledgement back, and let's say the time is like 0.4, well then this timer can then be reset back to 0, and like when it sends the next packets, again let's say we've got the receiver, well of course this whole thing is the receiver, right, let's say it waits for, I don't know, like 1 second, right, that can be our timeout. And if it's waited for 1 second and it's not received anything, well then it can of course send again, right, and then if this time it does actually receive a positive acknowledgement, again then it can just reset the timer back to 0. So it's just going to keep doing this, right, resetting the timer back to 0, yeah, whenever it gets a positive acknowledgement like that. Right, so I'm not going to write the whole thing because, well, honestly, it's 8 marks. It's going to take too long. I mean, let's just do it in bullet points. So, right, what we can do then, let's say the sender, right, sender calculates, right, odd parity, let's say OP, right, by counting, right, number of ones, right, in, well, let's say original data. Right, let's say if num ones right is odd, right, then let's say 0 will be set. Right, so 0 will be set, right, as, well, let's say PB, parity bit. Right, else then 1 will be set as PB. Right, okay. So again, right, if the number of ones is odd, right, a 0 will be the parity bit. If the number, well, yeah, else if the number of ones is even, right, then a 1 will be the parity bit. We can say maybe the sender starts the timer, or well, let's say sender sends, or let's say sends data, right, yeah, and PB, right, and parity bit, right, and starts timer. Right, then we say, well, the receiver. So let's say if, right, if receiver, right, so let's think of the different scenarios. Well, the first one can be if they receive it and it's correct. So if receiver, yeah, receives data, right, and let's say parity check, right, is odd, or yeah, parity check, is correctly sort of odd parity. Right, okay, parity. Right, then, okay, well then the receiver sends, let's say, well, positive, let's say P acknowledgement, right, positive acknowledgement, right, back to sender. Right, and then we can say, yeah, okay, right, let's say sends it back to sender, right, who will reset timer. Okay, reset timer, let's say back to 0, right, and resend, or well, not resend, right, yeah, and send the next data. Alright, so we've said then what happens if it's successful. Now, I did just check the mark scheme now, because, really this next part depends on the implementation. Like, if there's an error, so let's say if it's not odd parity, or yeah, if the odd parity failed, then of course you could have it where the receiver then, actually tells the sender, hey, this failed, resend. But I think in this case, because they're specifically saying, well, positive automatic repeat, repeat request, then what that's going to do is that, well, basically it's only going to send the positive acknowledgement, right? It's only going to send something if it's successful. Yeah, the receiver will never send, hey, this failed, send it again. And the way that the sender will know if it failed is, well, of course, if they don't receive the positive acknowledgement, right, after the, set timeout. So yeah, let's try and write that. So let's say, right, if, if packets received, or let's say if packets receiver received, right, if packets received are not, or let's say not on parity, well, I mean basically, like, I don't know, nothing will be sent, or receiver won't send anything. Right, let's say sender will wait. Or let's say sender waits until timeout. Again, let's say this timeout is, I don't know, like 1 second or 2 seconds. Right, sender waits until timeout. Right, and if no, right, let's say if no positive acknowledgement, right, then we'll automatically resend. Right, automatically resend. To receiver. Right, and then I guess what we can do, we can say, well, this process continues either until all the data is sent, or until maybe they have some, like, let's say, like, maximum errors, right? And let's say, like, if we have this, I don't know, where if this thing happens, like 10 times, right, then it just stops, because that might be while the receiver is offline, you just can't contact them, in which case, of course, there's no point sending data, like, if there's some I don't know, if there's some fault in the network, or if that device has been turned off. Right, so let's try and say that then. Process continues. Right, process continues, right, until all data sent, or let's say all packets sent. Right, or and let's say max errors exceeded, or maybe max tries exceeded. So we can say tries. Right, exceeded. And I mean, hopefully that's enough, at least for maybe 6, 7, or possibly 8. I mean, this question again, definitely check the mark scheme. Okay, make sure you understand what they're saying. And well, obviously, if you don't understand it, just ask in the comments, and hopefully I'll try to explain it. Right, so give 2 other error detection methods that could be used. Right, so I think here we can just say echo check. And just to recap, well, an echo check, that's where, let's say, A sends to B. So let's say they send the data, 1, 2, 3, and then B will just repeat that data. So it will then so let's go here. Right, this 1, 2, 3 is being sent from A to B. Right, this 1, 2, 3 is being sent from B to A. And of course, well, if A gets the same data back, so A goes, well, does 1, 2, 3 equals 1, 2, 3? Of course, if they equal, well, then it knows that B has, probably got the correct data. And I mean, the reason I say probably is because, like, let's say, for example, I don't know, maybe there was some error here, and I mean, this is going to be quite a sort of rare situation, but let's say there's an error where this accidentally transmits as like 1, 2, 4. B then receives this 1, 2, 4, but then when B sends it back, well, they also, I don't know, there's also some error where again it also transmits as 1, 2, 4. But I don't know, like when A receives it, of course it goes back to 1, 2, 3 because there's some other error. I mean, that's going to be a pretty rare situation, to be honest. So yeah, like if this echo check works, I mean, you can be sure, probably like, well, 1 out of, like probably it's only going to not work like 1 out of, a trillion times. Right, so yeah, let's say an echo check, and then I think we can probably also just go checksum. And of course, a checksum, well, that's going to be where it calculates, well, obviously, it just, does some algorithm based on the data. And then, well, it's going to generate like a hash value or a digest. And then the receiver will just check to make sure that that digest matches the digest that, A sent. So well, again, for an example, let's say A, right, B. Let's say we're sending the data, I don't know, like 1, 2, 3. Now, of course, this is going to be a lot longer. Let's say A does some checksum, and I don't know, we get the value like A7, 4 or something. So it's saying, well, this data is then going to hash right to this A7, 4. And of course, the real thing, well, this data might be, like sort of like thousands of bytes, or like megabytes, gigabytes. But this hash is going to be relatively short. Okay, that's why we use it. And then, of course, what B does is, well, B then takes this data, 1, 2, 3, right, etc. it then recalculates the hash value, and if it also gets the same hash value like A74, right, then of course it knows that the data has been transmitted correctly. Right, the next one, the company owner also installs a firewall to help protect the network from hackers and malware. Right, explain how the firewall operates to help protect the network. Okay. Right, so what we can say then, let's say the firewall can either be hardware or software. All right, firewall. Right, yeah, let's say is for either, because I mean often you're going to have two. Or so either let's say hardware or software. Right, and I don't know, maybe let's say and can filter. Let's say filter slash block. Right, well let's say because we want to be specific, so let's say incoming, right, and outgoing traffic. Right, incoming and outgoing traffic, right, based on, let's say, certain criteria. Right, let's say e.g. So what we can say, right, e.g. Let's say a whitelist or blacklist of IP addresses. So when we say whitelist, well, this will be a list of allowed IP addresses, and then a blacklist, well, this will be let's say a list or maybe a range of disallowed IP addresses. All right, IP address. Right, could also be things like the port number, because I mean often specific processes will run on specific ports. So yeah, my memory is a bit bad. I think 21 is going to be FTP. Yeah, I think SSH. So I mean FTP, right, file transfer protocol. So let's say sending files, or well, let's say uploading files to a server, downloading files to a server. Now, we might want to block that port because let's say we don't want someone trying to access like the FTP process. Well, yeah, we might want to temporarily kind of deny access to that port, because we wouldn't want them like uploading and downloading files to our server. Now, of course, this should be protected with like a username, password, yeah, maybe like a certificate as well. Obviously to make it more secure. Or obviously things like SSH, again, logging into the server. So yeah, we might want to say certain port numbers are disallowed, right, to stop people accessing those processes. Again, we can also mention something like heuristics. So let's say, right, e.g., right, if, well, I don't know, maybe if an IP, right, is sending huge amounts of traffic. Yeah, I guess, well, sending, receiving, all right, sending / receiving, yeah, large amounts of traffic. Right, okay, so yeah, no, I think that's going to be the main ones, right? So IP, port number, heuristics. I mean, is there anything else we can say? So we said it's either hardware or software, so possibly that'll get us 1 mark. I think, well, sort of, yeah, block incoming and outgoing traffic. I mean, maybe block is 1 mark, right? Incoming and outgoing, maybe that's another mark. Yeah, based on a certain criteria, right? Possibly that's 1 mark. And then I think listing examples, I mean, hopefully this should be another mark. Yeah, so hopefully that's going to be enough for 5. Right, give 2 examples of malware that the firewall can help protect the network from. Right, okay, so I think one we can say, let's say like a, well, yeah, like a DDoS, right, or DOS botnet. So let's go, well, distributed denial of service attack. Right, denial of service. And let's just put in brackets, right, DDoS. Right, that should be big S. So just to recap, a distributed denial of service, this is where, let's say you have our server, you then have the sort of, well, the botnet, right, the zombie computers, and what they're going to do is, well, they're just going to send loads of requests to our server. And of course, you know, like here we've got 4, but I mean, this could be hundreds, thousands of computers. And, you know, maybe they're sending like 1,000 requests per second or 10,000 per second. So of course, our server is going to be getting, you know, thousands or like millions of requests per second, which is basically going to cause our server to crash. Right? I mean, if we don't have like a good firewall, or yeah, if we don't have a way of like blocking out this, you know, malicious traffic. And what this means then is, let's say you have like the, let's call them L, right, the legitimate user. Well, the legitimate user tries to access our website or, you know, our service. Of course, they won't be able to, because, you know, this server obviously is handling all of these malicious requests instead. Yeah, so that's obviously why you'd want a firewall, you know, protecting the server basically. Right, and then I think another one. Yeah, this is similar to what I mentioned, but I think we can probably just say spyware. Because again, let's say you have some spyware that's, you know, well, obviously it's infected your system and it's just sending all of your files back to some, you know, third-party like hacker server. Well, again, like if the firewall detects that you're sending, you know, gigabytes and gigabytes of data, particularly if you're sending it to like one particular IP address, then yeah, that's possibly an example of spyware, which, you know, the firewall might be able to detect. But again, you know, you've also got to think, well, how does it know if it's like legitimate like upload? Because, you know, maybe you're uploading some like 20 gigabyte YouTube video or something, or yeah, how does it know if it's, you know, malicious? Yeah, like a malicious spyware. So obviously, yeah, that's where it's going to be a bit difficult. And yeah, that's obviously where like a firewall is obviously quite advanced, you know, if it can actually distinguish those. Right, but yeah, it seems that's all. And guys, I mean, this video is quite long, but hopefully it's useful. And well, as always, any questions, just ask in the comments and I'll try to answer them. All right, so see you in the next video.